Dear students, we are now starting the third lecture for our fifth week for the course of communication systems. In this week's in this week's discussion, we were talking about different circuits, hardwares that are used to generate variants of AM modulation. In our previous lectures, we have discussed how AM signal is generated and how DSB signals are generated. In today's lecture, we will be talking about single sideband modulators, that is a generation of single sideband signal, and we will also be talking about the demodulation of different variants of AM modulation. For this discussion, we will not be discussing vestigial sideband VSB modulation, because as we have previously discussed that VSB is actually another type of SSB. The only difference is that for VSB we need to have relatively larger bandwidth, so filtering is kind of different for VSB and SSB, and all the other demodulation and modulation steps related to VSB and SSB, they are same. So there is no need to have separate discussion on VSB modulators. So let us start our discussion on SSB modulator. So if you recall the single sideband signal, so we discussed that in single sideband we actually suppress one of the sidebands as well as the carrier from the AM signal. So single sideband is generated by suppressing carrier and one sideband. So basically we need two important things. First thing is to suppress the carrier, which is done by balance modulator, because we know that suppressing carrier generates a DSB signal, which is important, which is actually the variant of AM in which you have suppressed the carrier. So the DSB signal is basically generated by a balance modulator. So the first step towards SSB generation is to use a balance modulator, so that a DSB signal is generated in which you have suppressed the carrier. So it takes input of message signal and the carrier wave and then generate the DSB signal. After that, we will suppress one of the sidebands. Either upper sideband would be suppressed or lower sideband would be suppressed. So that suppression of sideband is achieved by using a sideband filter. So we will be using a filter in order to suppress one of the sidebands. This diagram here, it illustrates how the suppressed sideband would appear. So we have for this particular case we have suppressed the lower sideband and left with the upper sideband only. So this becomes a upper single sideband signal. Sometimes we call it upper sideband. So USSB is also named as USB and LSSB is also named as LSB. Similarly, for second figure, this one we have suppressed the upper sideband, so there is no upper single sideband, whereas we are left with only the lower sideband. So there is only the lower sideband here. So this type shows the LSB signal. So by using a sideband filter, we can either suppress upper sideband or lower sideband to generate a single sideband signal. One of the important thing related to SSB modulator is that is the filtering process. As I mentioned, that we need to filter out one of the sidebands. However, we understand that the practical filters, they have a response which is actually deviates from the ideal response. So they cannot suppress sideband sharply like it is shown here. So they cannot suppress sideband this sharp. So that's why SSB signals can only be generated where this end of the band, this edge, does not contain significant information contents. So mostly we use SSB signal where the frequencies near zero, they do not have significant information contents. For example, speech signal. Speech signal has information content starting from 300 hertz to 3400 hertz. You can see that there is no significant information content from 0 to 300 hertz. So for such signals we can use SSB modulator. So if we use this, this is the double sideband and this dotted line represents the filter response. So we can easily filter out one of the sideband if there is no significant information content in the message signal. However, if there is significant information content in the message signal near zero frequency, like we get in TV signal, so SSB modulator, they become inefficient because of this requirement of physical filtering. So that's why we need to use VSB modulation in that case, so that we do not suppress the information contents which are at relatively low frequencies. So the bottom line is that we need to use a sideband filter to generate SSB modulator, but practically the most common generation is related to the two-phase SSB generation. So typically we use two stages to generate the single sideband signals. So so in first stage, first filter, it uses the sideband filtering. So it tries to remove that particular sideband, and then after another frequency shift of 2 units, we use another filter to remove the remaining unnecessary frequency contents which are available in that system. From this scenario, the most practically used SSB modulator is named as Weaver modulator or Weaver method, which is illustrated in diagram here. So in Weaver method, what we do, so if we have this spectrum of the message signal, so first we try to have a minor shift in the frequency which is equal to half of the message bandwidth, and then we apply the filtering onto that shifted version of the message signal. So in first stage of the Weaver method, we only use filtering to remove this sideband. You can see that after filtering you will be getting only one of the sideband, but still this signaling is actually at the low frequency, at zero frequency. After that we apply a frequency translation in order to take this spectrum to a relatively high frequency, which is C. So this is an example of two-stage filtering. In first stage we use a simple modulator to create a slight frequency shift as illustrated from this here to here. Then we use filtering to remove the sideband, and then we use another modulation to get the required frequency shift in order to take the signal to the desired frequency band. So this is the block diagram of the Weaver Weaver method. So you can see that at first stage we are applying this oscillator, this carrier wave with the frequency of W by 2. That means it will be creating the shift which is equal to half of the message bandwidth, and then we will be applying the low pass filtering so that one of the sideband is removed, and after that we apply a shift, a frequency shift which is equivalent to the shift related to the carrier frequency, so that at the end you get the overall message signal at the desired transmission frequency, desired carrier frequency. So this is the discussion related to SSB modulator. Now let us move on to the demodulation process related to AM modulation. So once the AM signal is received, So how we can detect the information, or how we can extract the information from the received AM signal. In order to understand the process of demodulation, you should realize that information actually resides in the amplitude variation of the modulated wave. So for AM signals, the information is actually related to the amplitude variation of the carrier, and eventually, in order to demodulate the signal, you need to recover the envelope of the signal, because the information resides in that envelope. So that envelope can reconstruction sometimes need synchronization, and sometimes do not need synchronization. So there are actually two types of detection schemes. One is called non-coherent detection or non-synchronous detection, and second is called coherent detection and or synchronous detection. Non-coherent means we do not need to synchronize the receiver with the transmitter. That is, we do not need any phase information for the demodulation process. For synchronous detection, actually we need to synchronize the receiver with the transmitter. That is, we need to have the phase information at the receiver side. This non-synchronous detection can be used only for the case where you are using the basic AM signal. The standard AM can be detected non-synchronously without any synchronization, because in that case we do not generally encounter any phase reversal. But in case of DSB and SSB, we know that there is phase reversal as well, and in those cases we need to have this synchronization, and eventually DSB and SSB, they cannot be detected non-synchronously without any synchronization. So they need to be detected using coherent detection or synchronous detection. In fact, all type of AM modulation schemes, they can be detected using coherent detection. So let me individually discuss both type of detection scheme. So let us start with the non-synchronous detection, which is called envelope detector. In envelope detector, as the name says, it actually detects the envelope of incoming AM signal. So how does it work? So this is a simple illustration of envelope detection. So we have this circuit diagram of envelope detector. You can see that the first stage of this envelope detector is a rectifier. I have illustrated it as a diode here. You can see that this is the AM signal, which is represented as Vin. So this Vin is actually showing the AM signal, which has the envelope representing the message information. So once this envelope this AM signal passes through this rectifier, for this particular case I have used the diode. So once it passes through this diode, so eventually all the negative cycles, they would disappear, and you would eventually end up with these positive cycles only. These positive cycles, they are passed through actually this RC filter here. You can see that this is an RC filter, which is actually which actually works as the holding circuit, because we know that the capacitor can hold charge and it cannot discharge instantaneously. So you can see that once this entire signal passes through this RC combination, so what you would see, so let's say the first cycle appears, so it will charge the capacitor. As it tries to goes down, the cycle goes down, the capacitor would start discharging. So you would see this minor variation here. It shows the discharging of the capacitor, but before the capacitor is fully discharged, the second cycle appears, because this carrier wave is oscillating at very high frequency. We know that the carrier frequencies is very high, so these sinusoidal variations, they are coming at a very high frequency. So before the capacitor is discharged, the second cycle appears, so it will again recharge the capacitor, eventually when it goes back to the negative to the zero side, so capacitor would start discharging, but before complete discharging, the new cycle would appear. So again the capacitor would discharge, so you would see this thick line at the output. So this sinusoidal variation would disappear. So at the end of the capacitor, this V voltage is illustrated here. This will appear as this thick line, which actually shows the variations which you observe at the capacitor. So you can see that these variations, they are now following the amplitude variations of this envelope. You can see it here, but it has some DC component as well and some ripples as well. So in order to block that DC component, we use a capacitor. A simple capacitor is here, and also this capacitor and resistor, they serve as a low pass filter to eliminate these minor variations which are occurring in this waveform. So these minor variations are removed by this capacitor and resistor C2 and R2 combination. So at the end you would be getting this waveform which is actually following the message signal. So hence you can see that this entire circuitry, it can easily detect the envelope from the message signal. So bottom line is that the envelope detector is actually a combination of a rectifier and a low pass filter. If you pass the incoming AM signal from a this combination which is called envelope detector, you will get the message signal at the output, and you can easily notice that this reconstruction of the message signal do not require any synchronization. If we try to use envelope detector with DSB or SSB signaling, in that case we cannot detect it directly, because in DSB signal there will be phase variations. In that case you need to have a synchronization with the incoming signal. So we use a local oscillator. So this is not the oscillator which is used at the transmission side. This is the local oscillator which is implemented in the receiver, but you need to synchronize, means match phase of local oscillator with the transmitter, so that you can compare it the phase variations from the message signal, and then you can use the envelope detector to detect the DSB signals. So DSB signal can also be detected by envelope detector, but it's fairly challenging because of this additional requirement of this synchronization and phase comparison. So in that case, the most commonly used version is actually called synchronous detection. What is synchronous detection? Synchronous detection is also a type of AM detection, where we can detect all possible variants of AM, whether it's basic AM or DSB or SSB or VSB. All possible variants of AM can be detected synchronously. So this detection scheme which I am going to discuss right now is actually the generalized, you can say generalized scheme of detection, which can be used to detect any type of the AM detection, AM signal, to detect any type of AM signal. So how do we do that? So how this detection is achieved? So actually this detection requires two processes. First thing is to multiply, this is multiplication operation here, multiply the whatever modulated signal you have with a local copy of the carrier. This is ALO, LO stands for local oscillator. So we have a local oscillator which is actually synchronized with the oscillator which you used for transmitter. So main requirement here is the synchronization. That means whatever phase you have in the incoming transmitter signal, that would be matched with the this oscillator signal here. So you need to synchronize. That's why we use the name of synchronous detection, or sometimes we call it coherent detection. The name is used because this detection scheme only works when the local oscillator is synchronized with uh, the incoming wave. So that is this is illustrated with this synchronization function here. So first stage is to multiply this copy of the local oscillator with the incoming signal. So what changes would it make in the signal if we multiply this local oscillator signal with this carrier wave, or incoming modulated wave? So let me first illustrate that thing. So for simplicity, I have taken this signal. So our modulated AM modulated signal is actually a DSB signal, which is represented by multiplication of xt, which is message signal, and cos omega ct, which is the carrier wave. Actually, the intent here is to show the working principle of this synchronous detection. So that's why I have taken a simple example of DSB modulation, but you should realize that this synchronous detection is not only applicable to the DSB demodulation, it is applicable to AM demodulation as well as SSB demodulation and VSB demodulation. The discussion here is actually I have simplified the discussion for the understanding of students. If you want to have a more detailed analysis, I would recommend you to go through the relevant section in your textbook, because that section contains discussion with a generalized AM form. So you would be able to comprehend how the a generalized AM signal is detected synchronously by using this process. However, for discussion in this lecture slide, so I have taken this simple example so that you can easily understand what is going on in this synchronous detection. So as I mentioned, that the first step towards the synchronous detection is simple multiplication. The first step is to multiply the incoming AM signal with this local oscillator. So this is the chosen incoming signal, which is DSB signal. So if we multiply with the local oscillator wave, so what we will get, the YT, which is shown here. YT is the result of multiplication. YT would be actually this xt multiplied by this local oscillator signal. So you can easily see that if we multiply the incoming signal with this local oscillator signal, we will get this cos square term, because the message signal also have this cos omega ct term, and local oscillator also has this cos omega ct term. So this cos square omega ct term can be decomposed into two parts by using a simple trigonometric relationship, which is 1 plus cos 2 omega ct plus 2. So you can see this yt is actually a combination of two terms, which are shown here, aloxt by 2 plus aloxt by 2 cos 2 omega ct. If you closely look at these two terms, you would easily notice that the first term is actually the scaled version of message signal. You can see that this xt is the message signal, ALO is a constant amplitude, so it's a constant number actually, and 2 is also a constant number. So this ALO by 2 is actually a constant number, whereas xt represents the message signal. So this first term is actually representing your message, as it is actually directly proportional to the message signal, Whereas the second term is kind of different because it also contains this cos 2 omega ct term. Having this cos 2 omega ct term represent that this term is at very high frequency, because omega c represents a carrier frequency which is a high frequency, and of course 2 omega c is actually double of the carrier frequency. So this term is representing a very high frequency term, whereas the first term is the message signal, which is the low frequency term. So in order to get the message signal, we would like to remove this high frequency term. So actually we do not need this high frequency term here. So if we intend to remove this high frequency term, what we should do, we should pass it using a low pass filter, so that the high frequency component is removed and you are left with the low frequency component here. So you can see that the next step in this synchronous detection is actually low pass filtering of filter bandwidth equal to the message signal, so that you can extract only the message signal, and all the high frequency signals which are present in that combination, they should be removed. So we perform low pass filtering with the appropriate bandwidth, so that you only extract this term which contains the message signal only. So this term, the second term, would be removed by low pass filtering, so it would become 0 after filtering. So eventually you would end up with this form, which is ALO by 2 xt, and you can see that YD, I have mentioned it YD as the detected output. So this YD is actually directly proportional to the message signal xt. So you would get the overall message signal at the output side, YT side. So this is how the local oscillator based synchronous detection performs the demodulation of AM signal. For description purpose, I have taken the example of this DSB signal only. However, you should realize that the same concept is applicable to all other variants as well, and in fact the textbook contains the generalized derivation for all types of variants, and I would strongly encourage all students to look at that derivation as well, because what I have shown here is actually the simplified version of that derivation. So this concludes the discussion on the demodulation of AM signals. So summing up our discussion, I want to mention that there are two types of demodulation: non-synchronous, which is actually based on the envelope detection of the AM signal, and non-synchronous detection can only be used to detect the basic AM signal, whereas the other detection scheme is the synchronous or coherent detection, which requires phase information or synchronization, but it can be used for coherent detection. You can easily see that the basic AM is actually easier to detect because it does not require any specific synchronization mechanism. So from hardware point of view and implementation point of view, the non-synchronous detection is very easy and convenient. So basic AM signal is actually very easier to demodulate. However, we have previously discussed that the AM signal, they are inefficient from bandwidth point of view as well as from power point of view, whereas the DSB signal has better power efficiency, and SSB signals, they have better power and bandwidth efficiency. However, they have drawback that they require relatively complex circuitry because they need to be detected coherently by using an additional synchronization mechanism. So with this, we conclude the discussion on AM detection. So now our last discussion would be related to the AM receiver. So the basic AM receiver, or in case where we want to have an RF signal received at the receiver side. So the AM signal would be implemented like this. So first thing, the AM signal is collected by using an antenna. So whatever RF signal is amplitude modulated, you have to collect using the appropriate antenna. Then your selector or you can say the filters, they select the appropriate frequency band what you want to collect, because the antennas actually they collect a range of frequencies, so you generally need to select the appropriate frequencies. Generally the received signal strength is relatively low, so in order to get a stronger signal, so before any signal processing we generally need to use an amplifier. So immediately after an antenna we use an RF amplifier, so that we get a relatively stronger signal at this demodulation side. And then we use an appropriate demodulator to demodulate the signal, and eventually that demodulator removes the carrier and gives the signal at the output, and that output signal is actually fed into the audio amplifier in order to increase its power, and then it is delivered to the speaker, so that you get the audio output at the output side. So this is the basic implementation of an AM receiver, where you have these 4 stages before the overall signal is delivered to the destination. However, there is another implementation which is actually more commonly used, and that implementation is called super heterodyne receiver. I must have mentioned this term before, heterodyning. Heterodyning is actually a term used for frequency mixing, because the modulation and demodulation process, they require mixing of frequencies. So sometimes we use a term heterodyne, that means we are mixing the frequencies. So there is another receiver which is called super heterodyne receiver. What is the difference between this basic simple heterodyne receiver and a super heterodyne receiver? You can see that in the basic receiver we have only one demodulator where you demodulate the signal. However, in super heterodyne receiver is actually the receiver setup is implemented at 2 stages, or sometimes in more than 2 stages. So typically the receiver is implemented at 2 stages. There is an intermediate stage which is called intermediate frequency stage, which is generally for AM broadcast, which is generally taken as 455 kilohertz. So the basic RF signal which is collected by the antenna, it is first converted into an intermediate frequency stage, and after intermediate frequency stage it is again demodulated to recover the message signal. Using intermediate frequency stage provides significant flexibility in in hardware implementation, because number of channels which are used in that implementation, they can be combined at the intermediate frequency stage, and we have good signal processing hardware available for this 455 kilohertz based intermediate frequency. So what you have, so this is the illustration of super heterodyne receiver. This figure is actually representative of this super heterodyning. So actually what you do, you have an antenna which can collect a variety of different signals. There is a pre-selector or a filter, you can say, which is controlled by a local oscillator and a converter or mixer, or in other words, which is a modulator. Modulator is also a type of mixer because it mixes the frequency. So first we pass our signal through a filter to extract the required information. Then we demodulate it to a stage where you have an intermediate frequency, which as I mentioned, which is 455 kilohertz. So the first demodulation stage, all the signals, they are converted to this intermediate frequency stage, where you use intermediate frequency amplifier and selector, and whatever signal processing is needed generally is done at this stage, and eventually it is then again demodulated to the audio frequency. So from intermediate frequency stage to the audio frequency, we would demodulate it again to get the audio signal at the output, and before delivering to a speaker, we pass that audio signal through an audio amplifier, so that you get a significant amount of power at the speaker side. So this is the illustration of super heterodyne receiver, where you have two-stage demodulation. The first RF signal is converted to IF signal, intermediate frequency stage, and then intermediate frequency signal is then converted to the audio signal and delivered to the destination. So this is the overall implementation of AM receiver, that is used for reception of AM signal in different AM receivers. So let us conclude our discussion by taking a simple problem. So we have an standard an AM standard broadcast receiver is to be designed having an intermediate frequency stage of 455 kilohertz. So we have AM signal AM receiver which requires intermediate frequency to be equal to 455 kilohertz. You can see that the IF stage requires a local oscillator, so conversion from this RF stage to IF stage is based on this local oscillator which has certain frequency by using a specific mixer. And as we know that the mixer actually makes the combination of the frequencies, that is it creates a difference or sum of the frequencies. And of course, because when we are talking about the transmitter side, we are working on the making signal towards higher frequency, so generally we are interested in the term which represents the summation, whereas at the receiver side we are interested in the difference term because we want to reduce the frequency of the signal. So basically this RF signal and IF signal, these two frequencies, they are related to each other by this relationship. You can see that IF frequency can be either this carrier frequency, which is the RF frequency. Carrier frequency is the RF frequency and the frequency of local oscillator, or this IF frequency can be calculated using local oscillator frequency or carrier frequency. So these two are the relationship which are generated by this mixer. Mixer always generates this combination of the frequency or mixing of these frequencies. So we have the same situation in this problem, that we want to calculate the required frequency of the local oscillator. So we want to have the local oscillator frequency, so that the RF frequency 540 kilohertz is actually converted to this IF frequency of 455 kilohertz. However, we want to calculate this local oscillator frequency for two cases. For first case, we are assuming that the local oscillator frequency is above the frequency of received signal, and for the second case, local oscillator is below the frequency of the received signal. So this is the situation. We know the intermediate frequency, which is 455 kilohertz. We know the RF frequency, which is 540 kilohertz, and we want to calculate local oscillator frequencies for both cases where the frequency is above or below the received signal. And we know that The IF frequency is actually related with RF frequency by this relationship. Basically, the IF frequency is actually difference of the RF frequency and the local oscillator frequency, which can be represented in both ways, FC minus FLO or FLO minus FC. And from these two relationships, we can see that there are two possibilities. If we solve this case, IF frequency is actually FLO minus FC. In that case, local oscillator frequency can be written as sum of intermediate frequency and the carrier frequency. So the local oscillator frequency should be 995 kilohertz, that is above RF frequency. The received signal frequency was 540 kilohertz, whereas we need local oscillator frequency to be equal to 995 kilohertz. If you use the other relationship, which is local intermediate frequency to be equal to carrier frequency minus local oscillator frequency, in that case the local oscillator frequency should be written as FC. I'm sorry, it's a typo here. It should not be plus, it should be a minus sign. Typo. FC minus FIF. So if we subtract these two, this should be a minus sign here. I'm sorry for that. So FLO is equal to FC minus FIF. So it will be 540 into 10 raised to power 3 minus 455 kilohertz. So you get a local oscillator frequency to be equal to 85 kilohertz, which is actually below the carrier frequency. You can easily see that the local oscillator frequency is now below the carrier frequency. That means if we use local oscillator of 995 kilohertz or 85 kilohertz, in both cases we can convert the incoming 540 kilohertz signal to the intermediate frequency stage of 455 kilohertz. So you should understand that the local oscillator can have both possibilities. You can use the local oscillator of 995 kilohertz or 85 kilohertz. Both work the same way. So they both can easily convert the RF signal to the desired intermediate frequency stage. So this is the discussion related to super heterodyne receiving of super heterodyne receiver for AM reception. So for this lecture, we have talked about the single sideband demodulation, then single sideband generation. Then we discussed the synchronous as well as non-synchronous detection of AM signal, and then we talked about the AM receivers, both simple form of receiver and the super heterodyne form of the receiver. So this concludes our discussion related to the AM modulation. We have covered all major aspects related to the AM modulation and its variants. So we conclude our discussion here. Inshallah, in next week's discussion, we will be talking about other modulation schemes, that is the angle modulation. I mean frequency and phase modulation, because the angle modulation is a combined name for frequency and phase modulation. So we stop our discussion here. Thank you all.